Well, it's my pleasure to introduce our first keynote speaker, Pratik Chaudhari. Pratik is an assistant professor in electrical and systems engineering and computer and information science at the University of Pennsylvania. He is a core member of the GRASP Lab, and from 2018 to 2019, he was a senior applied scientist at Amazon Web Services and a postdoctoral scholar in computing and mathematical sciences at Caltech. Pratik received his PhD in 2018 in computer science from UCLA, his master's and his engineering degrees in aeronautics and astronautics from MIT. He was a part of Nutonomy Incorporated, which is now Hyundai Aptiv Motional from 2014 to 2016. He is a recipient of the Amazon Machine Learning Research Award, the NSF Career Award, and the Intel Rising Star Faculty Award. So I am very pleased to introduce you to Pratik Chaudhari, and I am looking forward to his talk.
Thank you for that introduction. There should be a Good morning, everyone. Oops. Very happy to be here. This is my first trip to UMD, so I'm very excited to look at everything and learn. Today, I'll tell you about some results that might shed light into how neural networks learn. As a way of introducing you to how I began to think about these problems, let me give you a tiny bit of history. I am interested in autonomy. And what do I mean by autonomy? I mean that I would like to build robots that live in the physical world, interact with the physical world the way you and I do. And if this is the thing that you desire to do, then right off the bat, we need the robots to have certain kinds of capabilities. It is not a machine. It is not a computer that looks at data on a hard disk and makes predictions. It is necessarily something that has sensors, actuators, and some computational glue that joins them. Right? And to hit the point home, I wanted to show you this video. It's taken from the movie made on AlphaGo by DeepMind without any editing. And this is two commentators. They are trying to talk about the game that Lee Sedol, who was one of the good Go players from Korea. He was playing against the AlphaGo machine. The one on the right-hand side is actually a very accomplished American player. And you see that when this was right after about 3 matches, when AlphaGo had beaten Lee Sedol thrice, and it's almost about to beat him for the third time. And they're trying to say, look, we have this amazing machine that is so good at playing Go, which we thought was the hardest thing until now. What can a human possibly do to defeat such a machine? Not any human among the best ones that we have to play Go. You see, like he is saying so very nonchalantly, if you want to defeat a machine, all you have to do is pull the plug. Doesn't take very much more. And it's a very crisp remark, but I think there is a huge nugget of truth there. Machines that cannot respond to changes in the environment are not robots. They have a very narrow kind of intelligence, and we would like to engineer different kinds of intelligence. Okay. In the early part of my career, I was interested in the actuation part, the control part, and a lot of this work also went later into this company called Nutonomy that Michael mentioned. Began somewhere around 2011 in the campus. This is a video from the National University of Singapore's campus, where we were building some of the first urban mobility on demand systems. You click on a phone, an autonomous golf cart will come to where you are on the campus and pick you up. Proof of concept demonstrations from those times. And a lot of that work was incorporated and grew into Nutonomy, where we were interested in solving problems of the kind. You and I, when we drive in the city, we follow the rules of the road. But all of us know that in order to reach somewhere on time, you have to break a few rules. The car in front of you is too slow, you have to go into the other lane and go ahead. It's just broken down. You have to go into the other lane and make progress, and you break rules all left, right, and center, but while being somehow very conscious about which rules you are breaking. You never hit lampposts, but you are perfectly happy to break over speed limits. Right? And the driving manual that we all religiously followed when we took the test is a codified language, if you will, of the rules that we ought to not break. We were taking these kinds of rules and then translating them into first order logic, LTL, linear temporal logic, to be specific, and then building motion plans or building trajectories that respect these rules and also have an understanding of which rules to break by imposing some kind of a hierarchy on these rules. Okay. And this kind of things do work. So we got pretty good results. We were able to deploy these results in the real world. But through this time, I felt more and more that it is not control that was the bottleneck to autonomy. It is really perception. Not because control is easy, but simply because we've been working on control for a long time now. And really, like if you think deeper about this, like the key reason why we cannot do good perception is that we don't know how to model the real world. There's many cars around you. When you're driving on a freeway, you have no idea what they're going to do in the next second. You have models, you can track them with sensors, but your sensors are not very certain about the state of the world. You don't know the intent of the person. You cannot even have a sensor for these things. You would try to estimate where the car is moving, but there would be latencies, and that would be the difference between you hitting that car and you not hitting that car. Right? At the end of the day, the algorithms that we have to reason about the unmodeled characteristics of the world and the uncertainty of the sensors are very fragile. A classical example is we have the nicest LiDARs right now. They will see as far as 300 meters, but then you're going to get 3 points from a LiDAR return on a car that is far away. And if one of them is missing, you're not going to call it a car. You're going to call it a person instead, or a tree instead. So and this is reality. It is not because we are particularly bad at using the sensors. This is how sensors work. This is how physics works. These are fundamental limitations to how we get to see the world in robots. Clearly, you and I don't seem to be so affected by this, right? We live perfectly fine. We are way better than any robot that all of us have built before. There has to be some reason. Let me take one example. So let's take computer vision as an example. All of you have 2 eyes. Roughly speaking, a good rule of thumb is each of your eyes sends about 10 Mbps information to your brain, B with a capital B, so that's bytes. Your brain is processing 20 Mbps, which is probably faster than the Wi-Fi in this room, each second. Yeah, this information is very, very low power. A fraction of a watt is what it costs to operate your 2 eyes. You have a huge field of view. I can see everyone around you, around in this room, and it is extremely rich data. I know the geometry, I know texture, I know semantics, and all of this is directly only through vision. Yep. On a typical robot, we would have many different kinds of sensors to ask such questions. So vision is great. We would like to use vision to build robots. Famously, an entrepreneur in the Silicon Valley says only vision is necessary to build robots. Teslas only have cameras. They also threw away the LiDAR recently, the radar recently. The key problems with vision, however, are that this data is extremely high dimensional. So if you have the same object, so this is a very classical picture, a very classical picture of one object with images taken from many different viewpoints, and you can get essentially an infinite number of images of the same object from different viewpoints, across different illumination changes, across occlusions, across different quantizations, name it. And we do not have good ways to model all this variability. Okay, this is where the buck stops. How does the brain do it? Well, the brain also doesn't do it very well. Yeah. So this is a picture of the human brain, and I took it from the papers of this professor called Van Essen. He was among the first few people to start mapping out the different functional areas of the brain. In the early 90s, people did this for monkeys. In the early 2000s, they managed to do it for the human brain. And you will see that such a large part of the human brain is dedicated to vision. About 30% of the gray matter is processing vision. At any given point of time, you're not listening to what I'm saying, you're actually watching stuff that is moving around you. Yeah? So it is not as if the brain is doing this very efficiently in terms of actually dedicating hardware to it. It is doing it energetically efficiently. Yeah? And in a sense, like this is the reason why people are interested in learning away this variability. There's a lot of variability in the world. You cannot have good models for all this variability. The brain is one example where learning can be thought of as a way of mitigating this variability, and this is why people began to get very interested in computer vision and learning. This is also why I personally got interested in computer vision. And that brings me to the second part of my career, roughly speaking, where I was interested in asking questions of the kind, what properties of the physical world allow us to learn efficiently or well? Okay. We know biological learning is efficient in a certain way. We know artificial learning is efficient or effective, at least in a very different way. What are the properties of the world that allow us to learn? Clearly, we are not allowed to learn arbitrary problems. We shouldn't be allowed to learn arbitrary problems. There has to be some theme. Yeah. And if you ask if you work on these problems, there is two big questions that people like to ask. The first one is why can we train today's neural networks well? Neural networks are very large objects. They have millions of weights, millions of parameters. You need all these parameters because you have to model all the variability of real data. Now, if you have such a big problem with so many parameters, so much data, because we would also like to capture the variability, the questions we ask to the data are also a bit complicated. So you're not just interested in cats and dogs all the time. You would also like your model to do segmentation. You would also like your model to do detection. You would like your model to reconstruct images of the brain when you register an MRI to an atlas. You do all sorts of complicated tasks with these networks. And this is why the functions that we use in deep learning are not convex. They are not simple functions of the inputs and the weights. They're complicated functions of the inputs and weights. Now, anyone, ask your friend in chemistry, ask your friend in physics, they'll tell you that a non-convex optimization problem in 10 dimensions is hard. One of my friends got a PhD for doing one. So it's basically very hard and practical. It doesn't make any sense that we are solving problems of this scale today in deep learning and getting away with it. And this is the kind of question that I was asking during my PhD, me and many others. And the rough thesis of this line of work is that if you imagine the loss function of a neural network, it looks a lot like the Grand Canyon. Doesn't matter where you start, there is always the river below you. Doesn't matter which part of the river you fall in, is the same river. And yes, there is nooks and crannies on the way, but we have figured out by now little tricks to get around them. Okay? So training a neural network is a hard problem, a very hard problem, should be a very hard problem. But it is not as hard as a generic non-convex problem, and this is why we can do it. The second question that you should also be thinking about if you want to understand why neural networks work well is in high school, people told you that if someone gives you 10 data points, you shouldn't be fitting a polynomial of degree 15 to these 10 data points because the polynomial can be quite wiggly in regions where you do not have data, and that means that you will not get good predictions on new data. This is high school stuff. Somehow in deep learning, we don't seem to get affected by this. We love building large models, and this somehow seem to work genuinely better. They work better on test data, and it doesn't really make sense. It cannot be that the textbooks are wrong at such a basic level, right? So these are the two kinds of questions that I would like to shed light on, and in a sense, we should also ask ourselves, why do we care? So part of me is a theorist, and it is not as if the practitioners are waiting for answers to these questions. They are doing extremely well without knowing anything about these questions, way better than well, one would argue. But my goal or my conviction is that the success of deep learning is telling us something new about the nature of data. If we understand this success or where it is coming from, we might learn new things about data. And the simple way of appreciating this is that all these years we've been trying to build a microscope, a good neural network. These days we became very good at building this microscope. But the point was not to just build a microscope, right? To watch what is below it. And that is what we would like to do next. Okay. I'll give you two kinds of results. I'll give you a vignette of two kinds of results. And many people have been trying to ask these kinds of questions over the years, and we have attributed a lot of mystery and intrigue to these models in our efforts to understand them. Here is two peculiarities. So a few years ago, we noticed that at the end of training, you take a neural network, in this case for image classification. At the end of training, you calculate what is called the Hessian matrix, which is the curvature of the loss function of a neural network, the thing that tells you how quickly the loss function changes locally at a given point. And that matrix, whose size is number of weights times number of weights, it has a lot of zero eigenvalues. So this is a histogram of the eigenvalues, and about 95–96% of the eigenvalues are essentially zero. This tells you that no matter which place you end up at the end of training, 95–96% of the directions are locally flat, and there is few directions in which the loss increases locally, those directions you shouldn't be moving, and there is some where the loss decreases locally. Those directions would be the ones that you should move if you wanted to decrease it further. Okay. Now, a lot of calculations in physics will tell you that such regions are very rare. So imagine this room. I'm trying to draw a cartoon now. Imagine this room as the space of all solutions. The set of solutions that look like this, the set of wide solutions, these relatively flat regions, looks like the end, looks like a little needle in this room. If every single point in this room was a solution, then these kinds of solutions are a large deviations phenomenon, and they're as rare as finding a needle in this big haystack. Okay? It doesn't really make any sense that at the end of typical training we reach such solutions. Okay? We didn't know why, so we said, look, typical algorithms work very well. In fact, the test error of these models tends to be quite large if you reach these wide regions. So we can kind of tweak the objective to give us a wide region to begin with. So if f of w is your original training loss, what we were doing is we would smooth the original training loss with a Gaussian kernel. So G sub gamma is a Gaussian of bandwidth gamma, and this smoothing destroys all the non-wide regions of the energy landscape, keeps all the wide ones, and makes them easy to find. Okay, slightly different objective that you can use to train your neural network instead of the standard cross entropy loss. And this thing works well. So this is about 2 to 4 times faster than SGD, still some of the fastest methods I know to train neural networks, and that's nice. But it's very surprising that you end up in regions like this, even if they are so rare at the end of training. Okay. The next peculiarity. Oops. Yeah, the next peculiarity. So we noticed that when you typically train a neural network with SGD, the noise in mini batches is very pathological. We imagine that noise is some isotropic noise which allows us to move with equal freedom around the true gradient, but that is not how real noise is. The covariance of the mini batch, the noise in SGD coming from the mini batches, it is again a matrix whose size is number of weights times number of weights. It is very close to what is called the Fisher information matrix. It has a rank of about 0.5%, not 50%, about 0.5%. So when you have a neural network with 1 million weights, only about 5,000 dimensions is where noise allows you to move. All the other dimensions are being moved roughly by gradient descent dynamics. Okay. Now this is just a fact. You can do it. You can check it on a laptop. And in the language of physics, people will call such processes non-equilibrium stochastic processes, and they're quite exotic even in the world of biology or physics, because that indicates that there is some energy pumping mechanism that doesn't allow the entropy to go to the rate of reduction of entropy to go to zero. And this can lead to very, very exotic phenomena. For instance, we showed that when you stop training, the most likely locations of that are reached by stochastic gradient descent are not even the critical points of the training objective. So for the longest time, everyone was very worried that this is a non-convex problem, and then you won't find global minima, you will only find local minima. What actually happens is that you don't even find local minima. You can be away from the local minima if your step size is non-zero. Okay, so this is very spooky. It shouldn't be so, or we would rather not have it be so, but that's a fact. You can, the weights of a neural network never actually stop. Everyone imagines that the weights are this little ball that bounces and then it stops at some point, which is where the gradient presumably goes to zero. That doesn't actually happen. The weights can continue to evolve in a subspace forever without ever converging to a place. These are very weird stuff. And that is that is what we were trying to look at. So this is peculiarity number 2. The noise is very pathological. Yeah, and over the years there is many such let's call it theories or peculiarities. If you ask some people, they will tell you that neural networks have so many weights, so many parameters as compared to other machine learning models. This has to be the key reason why they work well. Clearly, this is what distinguishes them from other models. And maybe let's go back to high school or maybe undergraduate for a second and ask ourselves, I have a bunch of data. I fitted many parameters using this data. I clearly do not have enough information to constrain all those parameters. So why the heck should the unconstrained parameters matter? This is a very naive line of questioning. But that tells you that a theory that says that large number of parameters is the reason why these networks work well cannot be complete. Okay? If you ask some other people, they'll tell you, oh, we have architectures. These are really special architectures that capture something about real data. And this is indeed how people in computer vision were talking in 2014, 2015, saying, we love convolutions. They have all these great properties like scale-free nature, local correlations. Images we believe to have these properties, and that is why convolutions and the convolutional networks work very well. Well, in the last few years, transformers also work very well. They do not have these properties. They have different inductive biases. So it cannot be that the architecture is the only reason that allows neural networks to work well. And we could go around the room like this and point fingers at each of these existing lines of attack. But I would like to convince you at the end of this talk that the real thing that we are missing is the elephant in the room. It is the data. The data that we feed these neural networks on is rather special. It is special in ways that we haven't seen before. And that is what allows them to work well, and that is what causes all these other mysteries that we see from the outside. Okay? Cool. So I'll first describe a result which we presented last year in Baltimore, incidentally. It is titled, Does the Data Induce Capacity Control in Deep Learning? And capacity here, I mean in the learning theoretic sense. So we have too many parameters, but the data doesn't allow all those parameters to be fit very well. Okay. For a second, focus on the blue line here. The blue line is showing the principal component analysis eigenvalues of CIFAR10 images. CIFAR10 is a small data set, 32 pixel plus 32 pixel images, RGB, 3 channels. So there is 3072 eigenvalues. And what this plot is showing you is that the data is not exactly low dimensional. In computer vision, we've always believed that natural images lie on a low dimensional manifold. This tells you that it is effectively low dimensional. So the ratio of the largest eigenvalue, which is normalized here to 1, and the smallest eigenvalue is more like 8 orders of magnitude. If you imagine an ellipse that subsumes the point cloud of the images, this is an ellipse whose longest side is 10 raised to 8 times longer than the smallest side. Okay? That's a gigantically lopsided ellipse. That's just fine, that's just data. Effectively, most of the data lies in the first 100 or so dimensions, and that is the real dimensionality. Okay? So far, we haven't said anything about learning. What we showed, okay, maybe before that, I can tell you a little bit about why this makes sense. If you think about it, the long directions of the ellipse are directions along which you have the most salient attributes of data. So this is a picture from Plato's theory of forms, or that captures Plato's theory of forms. So the purest cats lie on one side of this axis, the purest dogs lie on the other side of this axis, and those are the salient things. If you look at the other dimensions, this is where the aberrant stuff lies. So the blue dog, there is very few blue dogs in the world. That would be along the thin directions of the ellipse. The sky, which doesn't change very much, would also lie in the tail. Yeah. So far, just a statement about the nature of data and a very coarse characterization of the eigenspectrum of PCA. Now, I'm sorry, this clicker is new to me and I'm screwing up. Okay. What we showed is that when input data is like this, then essentially any quantity that you can ever calculate inside a network, be it the Hessian, which is the curvature of the loss function, the Fisher information matrix measures the curvature of the output, how quickly does the entire output change when you change the weights, correlations of activations of different layers, correlations of the Jacobians of different logits. Every quantity that you can calculate also has an eigenspectrum that looks like this. The Fisher information matrix is the orange line here, and it also drops very quickly at the beginning of the head. Okay? We call such matrices, or we call such models, sloppy, and here is why. Focus on an eigenvector that lies somewhere in the tail. This corresponds to a direction in the weight space where I can perturb the weights by 7-8 orders of magnitude before I start seeing any appreciable changes in the output of the function. The Fisher information matrix is the sensitivity of the output to perturbations of the weights, and this is how tiny the sensitivity is. Okay, so this is the network with about 3 million weights, and it looks a lot like taking all this gigantic number of weights and then plonking them down on the table, and then whatever sticks. In particular, these few dimensions are the ones that are being used to make predictions by the model. It's a well-performing model, and all the others are tiny, tiny decorations that are improving your accuracy. So 10 years ago, you would be perfectly happy to fit a low dimensional model that captures this part of the spectrum and gives you your 95% accuracy. To get to the end, you need to fit all the other structure of the tail. Okay? But the cool thing now here is that nothing can overfit on this kind of data. If noise were to come and change this part of the spectrum, then it couldn't do very much. The network would be perfectly happy with this kind of noise. Yeah, so neural networks work well on new data, not because there is anything special in the neural networks, but really because the data allows you to fit without overfitting. This kind of data allows you to fit without overfitting. If noise comes and changes this part, you are perfectly fine. If there are perturbations to the eigenspectrum in this region, then we couldn't call it noise. We would call it contrast changes, or we'd call it out of distribution or some system. If the blue line was flat like this to begin with, then you would see the curse of dimensionality when you fit these models. You would need a lot more data because it is now spread in many, many dimensions, and you have to capture each of these dimensions. If the blue line were dropping like a rock over here, then it would be a genuinely easy problem, and you wouldn't be surprised as to why your model works well on that problem. Yeah? So in some sense, this decay, which is linear on a log scale, is the only interesting regime where you are solving problems that are tractable, in the sense that you can fit these models with relatively a reasonable number of samples, and yet you're solving problems of practical import that the data is interesting and complicated enough. Okay. What we have said doesn't seem to be very specific about neural networks. Many systems in nature are sloppy. So I'm giving you an example of what is called systems biology style mathematical model of a system called extracellular regulated kinase half, ERK half. So ERK half is a catalyst that promotes or changes how cells grow in cells that are called PC12 cells in rats. And it so happens that there is a protein that is called EGF. It stands for epidermal growth factor. When EGF has a large concentration, ERK half changes in spikes. So you'll see spikes in ERK half if EGF is large, and when ERK half has spikes, the number of cells grows. Yeah. So you'll take the same cell and it won't change its function, but there will be many copies of the cell when it grows. There is a different protein called NGF, which is called neural growth factor. And when the concentration of NGF is large, then you will notice that ERK half has a large concentration also. And if this is so, then the cells grow, but they distinguish from each other in their functionality. This is, imagine like early stem cells growing. So this is some kind of a model that systems biologists like to build, and they will collect data of the concentration of these kinds of proteins, and then they'll fit these mathematical models in the effort to understand how these things interact with each other. For us in the room, it is not very important why these proteins do what they do, but you should think of this system as a system of coupled differential equations. The output of the system is the stuff that we would like to regulate. The parameters of the system are the concentration of the different proteins or the kinetic rate constants of the different reactions. You take your pick. We are allowed to calculate the sensitivity of the output to changes in the parameters. And what I'm showing you here are the eigenvalues of the Jacobian transpose times Jacobian, which is actually the Fisher information matrix. And what you'll notice is that there is a few eigenvalues that are large, and there is many eigenvalues that are distributed uniformly on a log scale. Exactly the same picture as this last slide, just drawn in a slightly different way. But when a biologist sees a picture like this, they become very happy. They'll say that, look, we know that biology would like the circuit to be insensitive to many changes, and this is exactly what it has created. I can perturb many parameters in the system, and they would be correspond to the perturbations here, and my circuit still continues to work in spite of these perturbations. So a biological circuit is sloppy. It is sloppy because the Fisher information matrix looks like this. It is sloppy because, in hindsight, it ought to be sloppy because that way it gets to be resilient to changes in the environment. It's a beautiful question of control theory, which we are trying to do now, as to why did the circuit become like this in the first place. You have a system that interacts with the environment. It would like to perform its function or job in a resilient fashion to changes in the environment. We believe that every system ought to become like this when it adapts itself. Okay? And a biologist wouldn't distinguish this from learning. This is a natural system. Sloppiness is also quite common in artificial systems. An Ising model is a very classical model in statistical physics. It is a very coarse way to think of magnets. It consists of different spins, and different spins take values that are similar to your neighbors or different from your neighbors. Think of a graph and edges that correspond to which nodes are similar to each other and which ones are not. You are allowed to calculate the sensitivity of the probability distribution of the spins, of which way the spins point, as a function of how many edges there are or what are the values of the edges, etc. And again, those things are sloppy. So in physics, they have developed very nice ways of understanding these questions. I will not go into that now. But the moral of the story of this slide is that many things in nature are sloppy. It is a very prevalent phenomenon across physics, chemistry, and biology. Yeah. And we see the same thing in neural networks. You see the same thing in natural images, sounds, text. And I like to say that if you give me a data set that doesn't have this pattern, then I buy you beer. Haven't bought a beer yet. Here is one way to use these things. Okay? I will tell you what are called PAC-based bounds. PAC stands for probably approximately correct. And learning theory people will write down expressions of this kind. So they will say that allow me to think of a probability distribution Q on the space of weights. You can think of it as a large number of different neural networks. Little e of Q is the probability that you make a mistake on a test datum if you draw a model from this probability distribution Q. So it's a test error, is the probability of making a mistake on the test data. Okay? E hat of Q is the same thing except that you draw the data from the training set. So your Q ought to be such that it has small mistakes, and E hat of Q is small. And they'll write down stuff like this. E of Q is less than E hat of Q plus some complexity term. This is the KL divergence between Q and some prior P. And P is not very important here, so ignore that. But the KL divergence of Q and P tells you how many different models does Q puts its probability mass on. If there's a lot of models that I'm considering as my potential hypotheses, then I need requisitely large amounts of samples to distinguish between these models, distinguish between these hypotheses. And this is really what learning amounts to at its most fundamental sense. You have a lot of hypotheses, you use observations and use data to restrict the number of hypotheses under consideration, and then at the end you get to pluck out one, right? If you have many hypotheses you put your mass on, then you need lots of samples also. And this is very old stuff, 30 years old in this exact form. But recently, when people started to plug in numbers into these kinds of inequalities, they noticed that typically for training in neural networks, the training error is 0. The test error, let's say, is 0.05 or something. So 5% chance that you make a mistake on a test datum. But the complexity term is much larger than 1. It's more like 100. And it doesn't take a theorem to convince someone that the probability of making a mistake on something is less than 100. It is just true by the axioms of probability, right? So this is why there is a lot of anguish and a lot of grief in the deep learning world, because all the stuff that we know from learning theory doesn't work. It doesn't hold for neural networks, and these bounds are vacuous. There are many bounds like this, they're all vacuous. Okay? And so there is again this big conversation as to clearly there is nothing wrong in how we derive these inequalities. Okay, this is pretty easy to do them. You can do it yourself. So there doesn't seem to be anything clearly wrong in the theory, but the theory doesn't work. What we showed in this paper is that if data is sloppy, then with just this much information, we can calculate an analytical non-vacuous bound on the test error of generic neural networks. So for a 3-layer network on MNIST, the right-hand side, the entire right-hand side is more like 0.38. It is much larger than the actual test error of the model, about 5% in this case, or 3% if I remember correctly, but it is less than 1, and that's the cool thing. Okay? So in a sense, this tells you that you don't need new theory to understand neural networks. The old theory works perfectly fine, but you need to appreciate the fact that you're not fitting arbitrary data, you're fitting data that has specific patterns. It has a large, the ellipse that subsumes the data is very lopsided, and the labels are typically correlated with the top parts of with the salient features of the inputs. Okay? With just this much information, you can have good bounds. We also improved these bounds numerically. It's not that important at this point. Okay? But one take-home message from this kind of analysis is as follows. So we can give you a quantity that characterizes the actual number of parameters or the actual degrees of freedom in a trained model. And mathematically, this corresponds to the number of eigenvalues of the Hessian that are larger than some threshold. Epsilon is not important again, but the denominator is 2 times the number of samples. And this is very clever, because if n goes to infinity, if I give you lots and lots of data, then this tells you that the network uses all its parameters. But if I do not give you all infinite amounts of data, and if I give you some small amounts of information to restrict all your parameters, then automatically the effective number of degrees of freedom that the network has are small. It is happening because of this peculiar shape in the spectrum, and roughly speaking, the effective dimensionality is the elbow of this spectrum. For typical problems, the number of degrees of freedom is less than 0.5% of the number of weights. So when people tell you that I am training a model with 1 billion weights, effectively it's a model with about 5 million weights or so. And someone tells you I'm training a model with 1 million weights, effectively they're building a model with about 5,000 degrees of freedom. Yeah? So real neural networks, the ones that we use, are much, much smaller than what we think. They're just large on a laptop. So here is a mental picture of the training process. What we have noticed and shown is that learning typically occurs along the top parts of the spectrum, the stiff part of the eigenspectrum, and those are the degrees of freedom that are fitted. when you begin learning. And the stuff that you do not fit are the sloppy degrees of freedom, are the small eigenvectors, but it doesn't matter because these eigenvectors do not play a big role in making the predictions. They're just decorations on the predictions. There's the difference between 96.2% accuracy and 96% accuracy. You're perfectly happy with 96 with even these parameters. Yeah. Over the last year, maybe we have been making this kind of a picture more rigorous. We call this shapes of manifolds hyperribbons. So the ellipse of the data that I talked about, it looks a lot like the hyperribbon in three-dimensional space. It's very long in some dimensions and then very thin in some other dimensions. This is also how the functions that we fit on these models, on this data look like. They are hyperribbons in some space of functions. This is a subject of two papers. The first one here will be presented at ICML this year. And the second one we put out on arXiv very recently. And allow me to give you a short exposition of this construction. It's rather peculiar and somewhat leads to somewhat surprising results. I'll start as follows. So a neural network is a probabilistic model. So it is a likelihood, which is P of y given x, parameterized by our weights W, right? Any x that I plug in, I get my output y from the model. You should think of ImageNet. ImageNet is a data set of 1 million images. Each image has 1,000 outputs, 1,000 different classes. So I'm allowed to plug in any image in it. I get 1,000 numbers y as my output. Okay. Now, the issue with understanding neural networks, this is really the crux of the technical part, is these functions are nasty. They are very large, it's an infinite dimensional object, and there is no nice thing you can do to understand it. We have been using a very cheap trick. It's a bit like you have a function f of x, you would like to understand what this function looks like, but you did not take a function analysis class because you were lazy. So what you actually do is you measure the function f at a fixed number of points and pretend that you have a vector. So if you have ImageNet, we have 1 million images in the data set. Those are the points at which you are going to measure this function. And every one of them has 1,000 outputs. So we get 1 million times 1,000, which is a billion dimensional vector. And this is now our function. Okay, we reduce the problem from thinking about an infinite dimensional object to a finite dimensional object, a very large object, billion dimensional vector, but finite nonetheless. Okay. Any model, doesn't matter how it was trained, if it has this exact same vector, then it is saying the same thing on this 1 million images. Okay, and this is really important. So even if there's a tiniest discrepancy in what two networks do in this billion dimensional space, then they are different. But if the two networks say the same thing, then they are same at least as evidenced by the samples in your training set. There could be other images on which they differ, but on these ones they are the same. Yeah. So there is one special point in this big space. It is what we call the truth. It is the one hot outputs for every image. It is the correct label. And in a sense, learning corresponds to reaching that point. This is the point that you want to fit on your training set, right? You begin typically in deep learning, people like to begin from the point where all the outputs are equiprobable. So the network predicts 1 over 1,000, 1 over 1,000 for every image, for every class. So in a sense, you start from complete ignorance about what the classes of each image are, and your goal is to go to the truth. This is training in its barest sense, but except that you're traveling between these 2 points in this billion dimensions. Okay. Once you define a space, this has a nice geometry. It is a product structure because of the independent images in your data set. You can now start defining geometry on this space. So we like to define geometry using what is called the Bhattacharya distance. You can think of it as symmetric K divergence. If you haven't seen this before, there is nothing very different going on. But the key point is that it is not a metric. And the reason for this is that in these dimensions, anything that you use to measure distances between points goes to hell pretty quickly. So we have to use things that are not metrics. and they do not satisfy the triangle inequality, and we get into all sorts of acrobatics and contortions to understand the mathematics here. And but the point of the fact of the matter is that these are things that are not metrics. And now we are going to do a very simplistic experiment. I'm going to train lots of models, hundreds of thousands of models, look at their big vectors in this space, and see what they have learned. The way you would do this is using something like principal component analysis. In principal component analysis, you preserve Euclidean distances when you project points from higher dimensions into lower dimensions. In our case, we are going to preserve the Bhattacharya distance between 2 points. So think of 100,000 networks being trained, and then I have a matrix now of size 100,000 cross 100,000. The entries of this matrix are the Bhattacharya distances, and I take an SVD of this matrix and then create a smaller set of coordinates in which I can put all these 100,000 points and watch them. Okay, this is the goal. Here is how the picture looks. So every point in this picture is one neural network. There is 6 different architectures, so fully connected networks, convolutional ones, small ResNet, large ResNet. This is a self-attention based model. These are all training on CIFAR 10. CIFAR 10 has 50,000 images in the training set times 10 classes for every image. So it is 500,000 dimensions, which is the actual size of the vectors, not a billion like ImageNet. All these models, when they start learning, they initialize at this point called P0 or near P0, which is complete ignorance, where the model takes 1 over 10 for every image. Okay, this is ignorance. You don't see truth in this plot, and I'll tell you why later, but all these points are heading to the truth. Okay, so they try to fit the one hot vectors. What you see here is that 6 different architectures trained with SGD, with SGD and Nesterov acceleration, with Adam, with different levels of weight decay, different batch sizes, different learning rates, different augmentations, about 2,300 different types of networks, about 150,000 different networks that I checkpointed during the training process. They all, in this 500,000 dimensional space, they all live in what is effectively a 3-4 dimensional manifold. So these are the eigenvalues of something like PCA, multidimensional scaling to be specific. The first 3 dimensions, which are the 3 that I have plotted here, capture 76% of the variance of this data. And this is very shocking. These are large models. Some of them have 40 million weights. They are living in this gigantic space, 500,000 dimensions. But they can be written down faithfully as using 3 or 4 numbers, which are the coordinates of this manifold. So networks, different networks, in spite of the gigantic diversity of these models, they learn similar things. They learn the same thing at the end when they fit the one hot probabilities, but they also learn it in the same way. A big network and a small network, they travel along the same trajectory in the space of probability distributions, except that the big one is a bit faster along this trajectory. So when people say that large models work well, it's not so much that large models work well, it's just that the small model wasn't trained well enough. If you were only to train the smaller model a bit better and progress it further through the non-convexity, it would work as well as the large model. And distillation, pruning, etc. are evidence of such statements. So this is a very stark picture of how low dimensional the actual optimization problem that we are solving is. We tell everyone that we are fitting a model with 40 million weights, and that is the dimensionality of the optimization problem. But secretly, we are solving an optimization problem of 3-4 dimensions. It is not an easy problem in these dimensions, even if it is only 3-4 dimensional, but because the aspect ratio of these problems is extremely bad. It's more like 10⁸. So you're not solving an easy optimization problem, but you're solving a low dimensional one, at least much easier than what you thought you were solving a priori. Okay? So the training process explores a low dimensional manifold, and different networks learn the same thing in the same way. We also know the reasons for the spray of points here. Adam typically causes these kinds of things, so it will lead to large changes in the probabilities. But the nice thing here is that these models are not stuck here, so they are just checkpoints during training, and just if you train them a bit furthermore, they will reach the truth. So all models in this entire plot, 150,000, they have zero training error, barring, let's say, a couple dozen. Yeah. So we have done a lot of analysis on this data by basically projecting it on 2 dimensions and then studying the different patterns that are arising here. So these are all convex models, for instance. They're a bit different from each other. There is another very weird thing that is happening in these experiments. Remember that this is each of these points corresponds to a 500,000 dimensional vector. The truth lies very far away from this manifold. The reason for this is that this is not Euclidean space, it is actually Minkowski space. So the second coordinate is a complex coordinate. And if you remember complex analysis, the distances in complex spaces, they go as delta x squared minus delta y squared if x and y have the same eigenvalues, right? So you should imagine that there is a light cone that juts out from P star. This is the light cone of special relativity that you might remember from high school. And all these points, they fall on the surface of the cone. So the blue points here are all points with zero training error. They're inching closer and closer to truth because the cross entropy loss never actually goes exactly to zero. It goes closer and closer to zero, but they have reached zero error a long time ago. Yeah. And this is happening for very mysterious reasons, but the points on the sliver of this manifold, let's say you pick a point here and another point here, these are big vectors but with tiny, tiny differences in them. So the visualization method that we have built, or the analysis method that we have built, it is able to pluck out anomalies in these dimensions. And this is completely absurd or mysterious. Why? We have a 500,000 dimensional vector, but we can find tiny differences in the probabilities just with this. I will end here, and I had a few more results, but we went through them quite slowly. Allow me to conclude. So the way we have been studying deep learning, by we I mean the community as a whole, has been to understand the weird properties that these networks exhibit. And along the way, we took a lot of missteps, and we attributed a lot of intrigue to these models. I believe that a lot of these properties are coming from the nature of data. The kind of data that we use is coming from the physical world. There are objects in the physical world. They have certain functions, they have certain semantics when they're close to other objects. And that allows us to learn well. It is not so much the networks, it is not so much the ways we train these networks or regularize these networks that is the reason for their weird performance. The second one is a little philosophical, and it's like I am very surprised personally as to why there is so much structure in natural data. And if you think a little bit about this, there is matter, there is molecules, and they are connected to each other via disorder. Why objects exist? So why do the molecules of iron give properties to the table? Why do the molecules of wood give properties to the table? Is a little bit of a question of physics. Condensed matter theory classically will ask questions of this kind. For us, we are interested in understanding what semantics we impose upon these objects. So we create objects with functions. We create objects with specific kind of function. The chair is something that you can sit on. And we don't go around creating learning problems that are arbitrary. So you take a bunch of molecules and you give it a name called a cat, because next time you will identify the same bunch of molecules in an easy way. You don't go around labeling leaves of trees because it is not useful for your tasks to give names to different leaves. So we created the learning problems for our sake. It shouldn't be that surprising in hindsight, perhaps, that artificial neural networks can learn these problems easily. These problems are learnable. If we had created problems that are not learnable, then we would see the difficulty of making the predictions. Yep. So I'll stop here and take questions.
Thank you for a great talk. So we started 5 minutes late on the keynote talk, so we have 5 minutes for questions before coffee. I'm going to run around with microphones for anybody. If you have a question, please raise your hand. I have a question to get us started. So you're learning on a kind of a low-dimensional manifold, but you don't quite know the important dimensions to start with, and they're probably, just because it's a manifold doesn't mean that any particular feature of the training data is what you're learning. But what does this say about potential for model compression if you go through the trouble of training on a huge dimensional data set? Are you able to kind of represent a model in low dimensions after the fact once you kind of know what the important subspace is?
Yeah. I think a very important question. So we know the names of those dimensions, roughly speaking. So at least the top 3 dimensions, we can interpret that as all the networks trying to fit the easy images at the beginning, the hard images at the end, and then reaching one particular point. So if you are shooting from ignorance to truth, the direction in which truth is one vector. The tangent to the trajectory at the beginning is another vector, and the tangent to the trajectory at the end is a third vector. These 3 vectors capture about 90% plus variance of all the points that I showed in that picture. And so this tells us that the reason the manifold is low dimensional is because the networks all learn in similar ways. They all fit the easy examples, first the hard examples later, and then in the middle there is a little more variance. The nature of data, the fact that data is sloppy, also has a bearing on the dimensionality of the manifold. The manifold will not look like this if the data is not sloppy. But to go to the second question, we can indeed take a trained network, write it down using 3 or 4 numbers, and that's a faithful description of that network on these images. It doesn't let us use that network on new images. And this is something that I'm trying very hard to do. It doesn't let me, these 3 numbers, I cannot use them for making inference on new images, which is in some sense what machine learning is all about, right? We can always compress the data in very nice ways. You can just delete your folder, and that's a pretty good way of compressing your folder. That doesn't help us recover the files. So in the same way, like the network is low dimensional, we know that a parameterization exists that is faithful. We just don't know how to exploit it yet. By we, I mean I.
Thank you for the answer.
Fundamentally, you work with very large vectors. Now, there is a field with a name, hyperdimensional computing. Another name is vector symbolic architecture, that they have developed a number of techniques over the years. Have you ever considered using hyperdimensional computing in your analysis?
I haven't. I did not know about this. So these vectors are very large, but the geometry of that space is pretty easy. If you think about it, the probabilities, output probabilities, they sum up to 1. So if I take the square roots of all the probabilities, they lie on a sphere because the L2 norm is equal to the number of dimensions. So the geometry of this space is a product of spheres. I can do all sorts of stuff in this space. Everything from a differential geometry textbook is up for game. You can calculate geodesics, you can calculate curvature of the metric, etc., etc. So we haven't, these are slightly simpler objects than what the size would suggest. They have very specific structure.
We have time for one more quick question, if anybody has a question. Okay. Thank you.
A very interesting talk, and your conclusion brought to my mind a question about you talked that it's not important to give the cat a name, and maybe it's more important to give the things a function. For example, if I train a network to identify chairs and then give a stair to the network, a stair is also a thing where I can sit down, but the network will maybe not identify the stair as a chair. And maybe this is an interesting point of view on the networks, not to identify objects, but to identify functions.
Yes.
What do you think about this?
Yeah, no, I think it's a beautiful thought. So Yanis would call it affordances. The objects are defined by what we do with them, not the names that we attribute to the objects. Today we build networks to classify the names. Of course, in robotics we want things that can give us the function. You can lift up this chair, you cannot lift up the walls. There are long-standing themes in computer vision, to be specific, where people have asked such questions. There is this notion of like David Marr had this called detachable objects, or detached objects, which are objects in the environment that you can move with your control authority, that gives that allows you to do specific things with the objects other than just interact with them passively. There is a I'm trying to think on the fly here. So there's a pragmatic way of thinking about the progress in deep learning, which is that we annotated this data with people who do not really appreciate the nuances of the definition that you proposed, and there is a way of exploiting that ignorance, if you will. The agency of a robot to move objects, to interact with them, allows it to learn the environment in different ways, but it is perfectly fine to bootstrap off this naive way of labeling objects.
Okay, thanks. Additional discussion and questions can happen during the coffee break. So let's give the speaker one more round of applause.